Lesson 9.5 is all about classifying functions and finding the classes of these functions. So let's jump right into it. The first one we're looking at is a constant function. Now remember, a constant function means it's not changing. It consistently stays the same throughout. So that's why it creates this horizontally straight line right here. Doesn't change over time, it just stays right where it's at. Now remember, a constant equation might include a vertical line. We would say then x equals, say like -5 or so. In this case we have y equals 1. But it's not a function because it doesn't pass the vertical line test. If we tried to draw a vertical line through it, it would hit more than one point. So a constant equation doesn't necessarily mean it's a constant function. Constant function has to still pass the vertical line test, which means we can only have our y equals as our constant functions. Another one to look at is direct variation. For direct variation, we just went over these. Remember, those are of the form y equals k times x. So, thinking of this intuitively, no matter what, if we plug in 0 for x, 0 times anything is still going to be 0. So all of these have to go through the origin, go through that middle point 0, 0. Otherwise, though, they are linear graphs, and their slope is just going to be equal to k. So whatever k is, that is then your slope of the line. So that would be direct variation. Then we have the identity function, which is a very specific kind of direct variation. It's where k equals 0, or not 0, k equals 1. So that would mean that y equals 1x, or you could just say y equals x. And if y equals x, that means we're including points like 1, 1, -3, -3, or 8, 8. Whatever you plug in is what you get out. Which means if we plug in 0, again, we get out 0. So it goes through the origin at 0, 0. So it's still technically a direct variation function. Moving right along, next we have the greatest integer function, which we've also come to call a step function. Now, greatest integer function, we kind of have taken to writing it with this double bar bracket here. You may also see it written as kind of a bracket underline piece here. That just means that when we look at it, we always round down. No matter where you are at, you round down to the nearest integer. So if we plug in 2.9 for our x value, that means that our y value is 2. Even though normally you round 2.9 to 3 because it's closer, we always round downward, never upward. So we round down to 2. Since we're always rounding down, that's why on our left side, each step is filled in. On our right, it's open, because we never quite hit that spot. We hit the next one up. Like I said, if it was 2.9, it would come down to 2. But once it goes to 3, then it's filled in. So that's why we have filled in on the less part, and it's open on the greater part. That would be our greatest integer function. The next one to look at is an absolute value function. And a big thing to remember with these is that they are V-shaped. So the parent function has a vertex right here at 0, 0, and it is possible to move that vertex up and down by adding something at the end of our absolute value, or left and right by adding something inside of our absolute value. It's also possible to stretch it either wider or narrower by multiplying something in front of our absolute value. So I'll do all of those at once. If we had y equals 2, absolute value, whoops, I'm going to do everything together. X plus 1 plus 3. Well, the plus 1 means that we're actually going leftward 1. It's the opposite of what you'd think. That plus 3 on the outside means that we're going up 3. So here would be our vertex. And that 2 means that we're going twice as quick as we grow. So instead of going up or over 1 and up 1. We're going over 1 and up 2. So our absolute value graph would look something like this. Our vertex has been shifted to the left and up 3, and it's going upward faster than before. And then we have quadratic equations, or quadratic functions, should I say, which is always, remember, going to look like a parabola. It has a vertex up here at our apex point, which is either the maximum or minimum value found on your equation. And as well, this a value is going to tell us whether it opens up or down based on whether a is positive or negative. Moving right along with some of these, we have a square root function, which is just like our quadratic equation, looks like a parabola, only it's tilted on its side. Instead of being a full parabola on its side, though, notice how a parabola on its side would not pass the vertical line test. It would hit the parabola at 2 spots. So we can't include all of those points, we can only include the top half, which is why it would be our vertex, and we're only including the top half of this sideways parabola. That creates a square root function. And again, like our absolute value function, we can shift that vertex up or down, left or right, and we can stretch it by multiplying something in front of our square root function. Next we have rational functions, and notice how they create horizontal and or vertical asymptotes. Now, a dead giveaway of a rational function is it's a fraction, and its numerator is a polynomial, and its denominator is a polynomial. That would create a rational function. So its graph would again look something like this, kind of almost a hyperbola effect with the 2 asymptotes going through there. Now, inverse variation is something we looked at before. That's where y equals k over x. Inverse variation is going to be a special kind of rational function where our top value, our top polynomial, the numerator, is actually a constant. So instead of being like x plus 2 or x squared minus 3, it would just be a value, say 2 or 1. In those cases, we would have an inverse variation function. Again, still having those asymptotes on there. And there's one other form of a rational function, and that again was where, let's say we had y equals x plus 4, x plus 3 over x plus 4, and we can cancel out these x plus 4s. That creates a hole at x is negative 4, because we had plus 4 for our x, so that it would be at x is negative 4 would create a hole. But it would act then like the line y is x plus 3. So in this case, here is our line that it's acting like, but we created a hole right here at, I believe that's x is positive 3. So that would be another form of a rational function. So let's just take a look at some of these examples here. All we're asked to do is identify the type of the functions represented. Well, again, here we can see kind of the sideways parabola, and it's only half of it. So we know that this is the square root function. And that's all we have to do for that one, is just identify it. So in this case, we notice we have a straight line with a hole through it. So the only thing it can be would be a rational function. Nice and easy. So moving along, let's say we wanted to use kind of a real-life example. We're saying Emily launched a toy rocket from ground level, the height above the ground level h in feet, after seconds, or t seconds, is given by the formula h of t equals negative 16t squared plus 80t, which graphs depict the height of the rocket during its flight. Well, we can notice that our function is a quadratic function because it has this, should I say f of x equals ax squared plus bx plus c, where c is 0, b is this positive 80, and a is this negative 16. So it is a quadratic. So we just need to match it with the quadratic function, which would be this one here. In this case, we are modeling the flight of the rocket. Again, identify the type of function and then graph it. Well, in this case, we have an absolute value of x, so it must be an absolute value function. Perfect. And we know that the parent function starts here at the origin and slowly moves out. But we also have to account for this minus 3, which means we're coming down 3 units. Otherwise, everything else looks the same. So it would look something like this. We're down 3 units from where we normally were, but we just continue to move outward. So this would be, I'll probably delete this. This would be the graph of our absolute value function there. Let's try it again one more time. We have y equals the square root of 4x minus 2. Now again, in this case, we can probably simplify that piece in there to say y equals, well, the square root of 4 is actually 2. So let's say 2 square roots of x minus 2. This piece here means we take our original parent function, which remember looked something like this. 4 and 1, 4 and 2, 9 and 3. So it went somewhere along these lines. That minus 2 means that we're bringing everything downward 2 places. So it's going to go along that line. But as well, we have this, oops, I should do that in blue, 2 out front here, which means it needs to stretch 2 from the vertex. So here it went from our vertex over 1 and up 1. Well, it should actually go over 1 and up 2 then. Here it went over 4 and up 2. Well, it should go over 4 and up 4, actually. Here it went over 9 and up 3. Well, it should actually go over 9 and up 1, 2, 3, 4, 5, 6. So, in the end, this is what our function should look like. It stretched 2 and went down 2. All right, in this case, looks like we have a polynomial on top and a polynomial on bottom. So we know that this is a rational function. It's easy to remember rational because it has the word ratio right in it. So these create a ratio. So first thing to do with rational functions is always see if we can factor them. We can factor our numerator, because it is the difference of squares, into x plus 3 and x minus 3. The bottom is already factored as much as it can be for us. And now we notice that we can cancel out that x plus 3. In doing so, that creates a whole at x equals negative 3. Before it was undefined at x is negative 3, because that would create a 0 in our denominator. But because we canceled both those factors out, it now just creates a whole. The line will still act like x or y equals x minus 3, because that was the last factor left here. So if our line looks like x minus 3 is our y-intercept, and it looks like our slope is just 1, so up 1 over 1, up 1 over 1, all the way, and down 1, left 1, all the way across. And the only thing to change now is that we have that whole at x is negative 3, so right about here, we have a whole. Now this is what our rational function's graph would look like. And that's everything from 9.5.